We'll start the session at 6:10. I'll just write it.
Wait, there is some special effects. बताइए क्या है? एक मिनट। टड़ा टड़ा टड़ा। ये तुम ही हो ना? इंडिपेंडेंट, खुद अपना ख्याल रखने वाली। जब घर पे अकेले बैठ के सोचती होगी तो ऐसी दिखती होगी। तुम्हें पता है, तुम्हारी लिप को लेके मैं बहुत कंफ्यूज था। फिर मैंने अपनी आंखें बंद की और मुझे ये दिखा दिखाई दी। तो मैं ले आया। That's my style. Now, would you accept this? Check out this one. साहिल कह रहे हैं कि आज ना हम यहीं पे रुक जाते हैं, तो प्लीज आप कोई ताने वाने मत मारना, और पापा आप भी प्लीज, ठीक है? मुझे कुछ कह देना पर उसे कुछ मत कहना। हमें तो कोई गिले शिकवे नहीं है, हमने तो उन्हें कब से अपने घर का मेंबर मान लिया। और लो जी बताओ, जा देखा जाके, नहीं विश्वास तो फ्रूट वगैरह सब देख कर आई हूँ। जा जाके देख कर आ, पाइनएप्पल ढंग से काट लिए, फिर तेरे पापा को भी दूं 2-4 पीस, बेचारे कब से वेट कर रहे हैं। और जी वेट करो। साहिल चलो यहाँ से। अम्मा खाने में।
अरे साला, इताल के फ्रॉड चल रहा है। फ्रॉड? कोई सा फ्रॉड भैया? अरे साला, इताल के फ्रॉड चल रहा है। फ्रॉड?
आपका नाम क्या है?
योगिता।
क्या?
योगिता।
आप इतना ही धीरे बोलते हो क्या?
नहीं बोल सकती मैं धीरे, मेरी आवाज।
आप मेरे साथ
कुछ ऐसे डिफरेंट बढ़िया डील।
बोलते बोलते बाबू इतना बोला।
तुम्हारा बाबू बहुत बोल रहा है।
ओले ओले बाबू।
रुको शर्म आता है, ऐसे मत बोल।
क्यों बाबू को शर्म आ रही?
यार मत बोल प्लीज।
क्यों?
यार मैं फ्लर्ट करूँ वो ठीक है, तुम मत करना सामने।
अच्छा क्या हुआ बाबू?
बहुत मजा आ रहा है यहाँ पे।
ओले ओले बाबू इतना बोला।
तुम्हारा बाबू बहुत बोल रहा है।
ओले ओले बाबू।
रुको शर्म आता है, ऐसे मत।
हाय मोहन।
हाय आरती, कहाँ से हैं आप?
हम लखनऊ से, आप कहाँ से?
मैं दिल्ली से।
अरे वाह, दिल्ली में कहाँ पे?
दिल्ली में गाजियाबाद।
गाजियाबाद दिल्ली में नहीं, यूपी में।
गाजियाबाद दिल्ली में ही है, मुझे मालूम है ना, मैं बचपन से रही हूँ। इनफैक्ट मेरे पापा का बिजनेस भी दिल्ली में है।
Okay, so we'll start the session. Let me just go to this. Hello everyone. So today we are going to discuss about the tutorials about the week 10 lectures that you might have seen. So hello everyone, I'm Balram Shah. I'm the PMRF TA for this course, that is Optimization Methods for Civil Engineering. So I'm doing my PhD at Interdisciplinary Center for Water Research at IISc Bangalore. So let's start with some question. Let me see. Okay, so before starting, let's start with the R code that we have stopped in the last week. So in the last week we have discussed about, yeah, so in the last week what all we have discussed, we have discussed about the genetic algorithm, how we can use, how we can do that, or how we can solve the optimization problem using genetic algorithm in the R software, right? So before that we have seen that some introduction to R. So we'll continue that introduction first, and then after that we'll move on to genetic algorithm, then some evolutionary strategies, and we also have learned that genetic algorithm is one of the meta-heuristic problem, but one of the evolutionary algorithm, right? Some other evolutionary algorithm are, uh, hello Nimai, Mr. Nimai, can you please switch off your audio, please? Okay, so what I was saying, yeah. So what all we have discussed in evolutionary algorithm. Hello Nimai. Okay, so what we have discussed about the evolutionary algorithm, and
হুম
one of them is the,
না হুম একটু পরে তোমাদের কি হচ্ছে
sorry. Okay, so we have discussed about the evolutionary algorithm, and genetic algorithm is one of the evolutionary algorithm that we have seen. Other than that, what all algorithm are there which is like comes under evolutionary algorithm? Those are particle swarm optimization, then others are there, right? So like that we'll discuss about the evolutionary strategies, and then particle swarm optimization, the introduction to particle swarm optimization, and how can we do using the R. Okay, so let's start. So let's start with the R code only, introduction. So in the last session we have seen, okay, I hope you can see the screen for, okay, the R1, right? So we'll discuss the introduction first. So what all we have discussed in the last session about introduction, that how we can create variable as a scalar quantity, how we can do some operations, right? Then how we can create a vector. Creating a vector or maybe an array we can do in several ways, right? So if you use C, then it will make a column matrix. You can say one vector, and this 1 to 5 means 1 2 3 till 5 it will go, right? And if it is like 5 to 1, it will start from 5 and it will go to 1. You can give the elements manually also like this. Okay, if you want sequence and you want the difference by 1, you can use something like that, right? If you want to do sequence with 1 to 5, okay, I'll show this. So you just run this. Here you can see we have run this, and here you can see that we have got the vector, right? See, okay, I don't know why it's not working. See here, if you see here we have got 1 to 5, right? Like that, if you run others, like if you want to run this E, so for I'll switch off the camera, otherwise it's having problem, I guess. Okay, so if we are seeing the E vector, how we can create that? We can create like with sequence from 1 to 5, but the difference will be zero 0.5. So it will start like 1, then 1.5, then 2, 2.5 and all. So if you just run, you can run this. The shortcut key is control enter. Okay, you can just press control enter and it will get run. Now you can see E has been run, and if you see this E, so here you can see it starts from 1, 1.5, 2, 2.5, 3, 3.5 and so on. Okay, and like that, yeah, you can create like this also. So these are some of the ways that you can create a vector using different ways you can write. If you want to know the element of D at second position, you can just write like this. Fourth element in the E vector, you can write like this. Okay, after that we have seen how we can create a matrix with three number of columns, three number of rows, two number of columns. Like that we can write. Okay, then we have seen C bind, R bind. What does this C bind do? C bind will create a matrix by binding two or more vectors but as column. Okay, so let's say if you have two vectors and you are binding it using C bind, then the first vector will come as first column, and the second vector will come as second vector will come as second column. Similarly, if you use R bind and if you have two vectors, then the first vector will come as first row and the second vector will come as second row, right? So like then you can use the R bind. We have seen matrix operation also. So in this, if you do A and you give the star sign or multiply sign B, it will only do the multiplication of the elements wise. Okay, so let's say the element in the first row first column will be multiplied by the first row first column of the second matrix, something like that. And if you want to do the actual multiplication, then we have to do something like this. Okay, after that we have also seen how to create a data frame. Why we are creating data frame? Because most of the work that we do and the data we have, that can and that is not only limited to numbers, right? It can be numbers, it can be real numbers, it can be date, it can be maybe text, and it can be so many other things. So for that we need to create data frame. Okay, and please note that whenever you are doing any operation process like this, if you are writing data frame, it should be written in this format only. Okay, so let's say if you are doing in Python, it will be a what? It will be D will be capital, F will be capital. You will see if you work with Python, you will understand that. So these variables and these functions are letter specific. Okay, whether if it is capital letter or a small letter, based on that you have to write. Okay, but when you are creating a variable you can create on your own, so you can write anything. Remember that in variables you can put special characters, right? Something like star or maybe and, if you are putting, you can write that in your variable. In variables you can write numbers, you can write letters, maybe capital letter, small letter, anything like that. Okay, so after that we have seen, after creating the data frame, if you want to see one element of the data frame, how you can see that? You can calculate the time difference between two dates, right? And all those. And we have also seen conditional statements. We have seen how we can use if else, how we can use only if, and we have also seen some multiple conditions, right? These are or, then this is not, this is and so on. Okay, after that what we have also seen if else condition, right? We have seen for loop, we have seen while loop. So now let's start with today. So we have done with the function, but still we'll go through those ones. So while doing the genetic algorithm, we have used the function also, right? So if you want to write any function, so let's say if you have a function fx is equals to x square plus 54 by x. Okay, and that you want to write in the r. So how will you write? You will use this function. Okay, so if you want to know that how we can write the function, as I mentioned, that you can go to help and you can just search here function, and you will get this. See, so you will get how to use that, what are the arguments in it, what are the details, and you can get one examples also. So here they have one run example function x, where the function is what, x into x square, right? Or you can see anonymous function z is the function. So here f of xy is z. Okay, so z is the function and x square plus y square is the function, and next function is x plus y plus z. So this is a matrix kind of thing. Okay, okay, so we'll see first with the single variable. So let's say we have only a single variable fx is equals to x square plus 54 by x. So how will we write? We'll consider some variable f1. So f1 we are considering as a variable in which we'll store the function. Okay, which function? That is x square plus 54 by x. So we'll write function bracket में x. So x is that variable, and if you don't write this also it's fine, but for now we'll, so because if we do for more variables, or if you are doing for maybe two functions, three functions, something like that, then it's better to use this curly brackets. Okay, so for one variable also I used to uh, follow the same, so that we can follow the same thing for every each of the functions that we write, right? So we'll use this curly brackets, and then we can write x to the power 2, this means x square plus 54 by x. So this is one function. Okay, so we'll just run this. We have run that, right? X square plus 54 by x, and here you can see the functions we have got as f1, right? Now let's say if you want to know that, sorry, so let's say if you want to know the value of this function, that is x square plus 54 by x at 1. So at 1, what will be the function value? X square, that is 1 square plus 54 by 1. It should be 1 plus 54, that is 55. So just run. See, we are getting how much? 55, right? Similarly, if you want to get the function, this function value at -1, so how will you do? Just, sorry, just do this, control enter. See, you are getting minus 53. So this one will be -1 square, that is 1 plus 54 by -1. So 1 minus 54, so minus 53. Okay, similarly, let's say uh, if you guys can do R now, it will be better. Anyone who will be able to do now, or else I'll just go through it. Okay, I'll just go through it, it's fine, otherwise it will take time. Okay, so let's say we are taking some other function. Okay, here also we are considering one single variable only. Okay, so the function is 2x power 4 minus x cube plus 5x square plus e to the power x. So e to the power x or exponential x, how we can write? You can use this function, that is exp. So exp, this means what? It will consider e to the power. Okay, so exp x. So if it is e x e to the power x square, so what we can write here? You can write here as e to the power x square, something like this. Okay, so let's say we have written this function. So is there any, like, you will be able to write the function, right, like this? Okay, so I will run this. Now if you want to know this function again at the value of 5, like at x equals to 5, what will be the value? The similar thing what we have, whatever we have done in the last function, we'll do that. Okay, just run. Because of ex square and all, it is coming so much. So let's say run it again. Okay, so at this function value we are getting 1394.413. Okay, so this one was the function for single variable. Okay, now let's say if you want to create some function with several variables, maybe more than one variables. Okay, then what we can do? Firstly, we can do, let's say if you have three variables x, y and z, so the function maybe, let's say f of x, y, z is x square plus y square plus z square. Okay, so in that case, how you can write? I'll just write it, maybe f fi, let's say fi. You can just write function again, and you have three variables, right? X comma y comma z, right? Now as I said, we'll follow similar approach. So just what was the function? The function should be x square, okay, x is square plus y square plus z square, right? So this is the function with three variables. But see, now here what I'm doing, I'm considering these three variables as scalar quantity, okay? So here we are putting all the three variables and then we are writing like this. So this is kind of scalar input. Okay, so if you run this, we have run this, right? Now let's say if you want to know this function value at some maybe some x equals to 1, y equals to 1 and z equals to 2, let's say. So how will you do that? So now here what we have done, here we have kept only each of the variables. So these are considered as scalar input. Okay, so just write fi at maybe x equals to 1, y equals to 1 and z equals to 2. So how much will be the value? It should be 1 square plus 1 square plus 2 square, that is 4 plus 5, it will be 6. Just run, see, we are getting 6, right? Similarly, if let's say if you have a two variable function and the function is 10 plus x1 square minus 5 x1 x2 plus 9 x square, sorry, x2 square plus x2. So you can write like this, that is f3 equals function x1 x2, x1 x2 are the two scalar inputs or the two variables. Okay, so just run this, control enter. Okay, so this one was how we can do the scalar input, right? Now let's say if you have a vector, okay, in which there are so many variables. Here we have written three variables, two variables, but let's say now you have 100 variables. So in that case, and you have that vector with all the 100 variables, okay, in that case what will you do? You'll directly take that, we'll directly take that and just put here. So now we'll see how we can use the vectorized input. So we are writing again, f4 is some kind of variable we are keeping, so that we are keeping the function in this. Now function x, here see, we have only written one variable and this variable is nothing but one vector, and this vector can have different number of variables. So in this, whatever we are writing the same function, right, but in some different form. So here x in third bracket 1, this means what? The first element of this vector. So let's say if x is a vector with two variables, that is x1 and x2. So x1 means what? X1 means, or let's say, okay, I'll just write it something like that. Let's say x is a vector, I'll write it as comment. X is a vector with, okay, with let's say uh, maybe a comma b. So a and b, x is what? X is a vector with two elements, that is a and b. Now if you write x, if you write x in third bracket 1, this means what? This means the first element of the vector x, and first element of the vector x is what? A, right? And again if you write x2 here, this means what? The second variable or the second element of the vector x. So second element is what? B. So x2 means what? X2 means b. Okay, so here let's say x is a vector with two elements, that is x1 and x2. So same thing we are writing, 10 plus x1 square minus 5 x1 into x2 plus 9 x2 plus x2. Oh, it should be x2 square, right? Okay, I'll write x2 square, x2 square. Okay, now I'll run this again. So see, now f3 is which one? F3 is this one. So this has scalar inputs. So at x equals to 1 or x1 equals to 1 and x2 equals to 1, what will be the value? It should be 16. If you just put it in this, x1 as 1 and x2 is as 2, you will get 16. Now the same function I have written in vectorized format, right? Now if we write this, so remember that how we can make a vector, it can be in this form, that c11 means what? The two, you remember here in the first here, see, we can write c means it will make a column. So with manual input you can write 1 2 13 4 25, like that only we are writing c11 means what? There are two elements with values 1 and 1. Okay, so if you are finding out the value, that is f4 is the vectorized input, right? Now we want to find the value of f4 at x1 equals to 1 and x2 equals to also 1. Then it should give the same value. Let's run this. See, we are getting 16, right? So I hope this vectorized input, scalar input, how to write the function and how to get the value of the function is clear. Okay, so with this we'll solve our first question. Let's say, okay, so write a R code to find the value of f of xy at 2 comma 2. Can anyone please do this and let me know the answer? Maybe I'll give 1 or 2 minutes. Let's see. Okay, so I'll do it once. Let me just do it. What is that? x1 square plus x2 minus 11. Okay, so we'll write this. Anyone has done? Okay, okay, fine. So we'll write that function maybe. So let me write at maybe f fq, let's say. Okay, fq is what? Function x. So I'm writing it as vectorized form. Okay, so what was the function? Function was maybe minus 11 plus x1 square plus x2 plus x1 square plus x2, right? And then, oh, it's a square, so square plus x1 square minus plus x2 minus 7, x1 square plus x2 minus 7, right? I hope this is correct. Square is there. Okay, sorry, square, right? So we have created the function as per the question, right? Now what is the question? Question was to find out the value of this function at 2 comma 2, right? So just what we have to do, fq at c of 2 comma 2, right? Just run these two lines and tada, you will get the function value. So the function value is 26. So the correct answer will be B, right? Okay, I hope this is clear. This was not that difficult. So now let's move to curve and AB line. So in the last class also we have seen that how we are doing genetic algorithm. In that we have plotted the curves, we have plotted the 3D plot, and then we have plotted the contour plots. So those we'll just go through once. So how we can plot a curve? So let's say you have a function. So curve will be for a 2D function, right? So we'll take with one variable, any one variable function, whatever we have, we'll take that. So here any one variable function we have written. Yeah, so we have one function. Maybe let's say if you want to plot f2 or f1, anything we can plot, right? So we'll plot maybe f2 only. Okay, so f2 is there, and the limit for x we are keeping at -10 to 10. Okay, and there are no more points we are keeping as 1001. Let's say you can change this. Okay, and we are giving the label of x as in the name for the x axis we are giving as x, and the name for the y axis or the label for y axis we are giving as f of x, and the color equals blue as in the curve for this function, that is f2, will be in the blue color. So just run this. See, you have got a plot. So this is the plot for which function? This is the plot for the function f2, and f2 was what was f2? F2 is 2x to the power 4 minus x cube plus 5x square plus e to the power x minus 4. So because of this e to the power x, the value is from 0 to maybe 40,000, I guess, right? So we'll also plot curve for maybe first one, that is f1 is what? F1 is x square plus 54 by x. We'll plot this also and we'll see how the curve looks like. Okay. So we'll f1. So let's say now I want to change the x-axis or the limits of x-axis. So the upper bound, lower bound will give -5, and this one may be at 5. Okay, and just plot this. See, this is the function for the function, that is x square plus 54 by x. So it will something look like something like this. Okay. Now, so let's say we'll plot the first one only. Okay, and now come to AB line. What is AB line? So here A and B represents the intercept and the slope. Okay, so it is like, if let's say if you have a straight line y equals to a plus bx. Okay, so let's say I'll write that as comment. So let's say you have a line that is y equals a plus bx. So here a is what? A is the intercept, and b is what? B is the slope. Okay, so we'll come to that. Now AB line does what? AB line will create some lines on the curve that you have plotted. So here what, see what I have written, AB line v equals 1. So v equals v, from v we can understand it's vertical line. Okay, and 1 as in at x equals to 1, at x equals to 1 we will get a vertical line. Okay, and the color we are keeping as red, let's say. So control enter. See, we have got at x equals to 1 we have got the line. Now see, if we are writing maybe, okay, h equals to 2000, in this curve we don't have, oh we have. So h is what? H is the horizontal line. So horizontal line as in we'll have one horizontal line on this. So now let's say you want to create one horizontal line at 10,000 value. Okay, so we'll write h is equals to 10,000 and just plot that. See, at 10,000 you got a line. Similarly, as I said that AB line, A represents what? Intercept, and B represents what? The slope. So that, like that also we can write. So at some intercept of 1.5 and some maybe slope at 2000, at slope equals to 2000 we can plot that. Okay, or maybe if you want the intercept at, let's say 5. Okay, and just plot it. See, we got the intercept will be at 5 and the, sorry, the slope will be 2000, and this line will be coming like that. Now if you just want to put a text in the plot, you can just do it like that. Okay, so wherever you are doing, based on that you should put this values, that maybe let's say I can write it as 5 only. Let's say where it is plotting. Okay, so color equals to 6 again. So there are different colors, right? So this sixth color will be coming. Okay, let's just plot. Okay, so it is maybe after so much, so we'll just write it as minus 0.5 and let's just plot it. So we are getting something here. So based on whatever value you are giving, based on that you will get the text. Okay. Okay, now again let's say if you want to plot one more curve but in the same plot, then what we can do, we can so we are plotting f1 function. So we have plotted f1 function before. So how it will look like? It will look like something like this. right? Now you want to plot this plot on the same plot, so on the same curve in the in this plot. Now you see the limit we have given as minus 10 to 10. So minus 10 to 10 is the x-axis, but the y-axis will be very small. So let's say just if you just plot this, see, you can see line here, it will be something like this. Okay, we'll change that. mm, Maybe on f1 we'll plot f2. Let's see. V equals to 1 maybe we'll plot, and h equals to maybe at 2000 we'll plot. Okay, and let's say if you want this AB line, let's see, it will be something like that. See here again text is very less, we have to reduce that. Okay, and now we want to plot f2, not the function f1, on the same plot. Okay, just let's see. So see, at x1 or my equals to, or x equals to minus 4 to 4, it will be something like that. Okay, but as the value is only 2000, it will go like this. You have seen in the last one, right? If you just want to change the color, you can just change it from here. Control C, the color has not changed. Oh, sorry, the text color I changed. Sorry. Okay, so how we are doing that? You can see one more argument. So the argument is what? Argument is add equals to true. So what we are doing here, we are adding this function, that is f2, in the same plot that is there. Okay, if you have plotted maybe 2 3 curves in the same plot, and then you want to add one more, so you can just use this argument, that is add is equals to true, and it will be added in the current plot that is there. Okay, so just change the number here, maybe 7. See, the color has changed. Okay, based on that, whatever color is there, so color has changed to black. Maybe we'll keep something as 8. Okay, 8 is gray, we'll keep 6. Okay, so this is done with the curves and AB line. Okay, so AB line, what it is doing, it is plotting several lines, right? Even if it is having a slope or intercept, we can plot that using AB line. Whereas curve is doing what? Curve is plotting the function. So any function that we have, we can directly write it here also. Even if we are not mentioning the function as function, you can write x square plus y square here. So let's say if you want to write that also, I'll write that. Sorry. So let's say now we want to plot, um, what do you want to plot? Maybe x plus x square, add equals to true. Okay, I'll change the color maybe at 5. Okay, it's very small, so you can't understand that, so we'll write it as maybe x is cube plus x square, and then we'll run. So you can see that also here. It's, if you zoom it, you will understand. Let's say, see, one line is here, this is the second, that is x square plus x cube, just now we plotted, and this is x plus x square. Because of the y-axis is very large here, because of the function that we have created, that is x square plus 54x, and because of that we can't see this. Okay, so because of this limits, you can't see this. Okay, now coming to the 3D figures. So any question till here in curves or AB lines in the 2D plots? Okay, if not, we'll move then. Okay, now coming to 3D plots. So 2D plots we have just seen. Now coming to 3D plots, 3D plot can be done in the 3D way, like what we can see or visualize. Again, this 3D figure can also be shown in what format? In contour format, right? So both of them we'll see. So let's say we have a function. Again, for 3D figure we need two variables. So if there is any two variables in a function, this means it will create a 3D figure, right? So now let's say we are creating one function with two variables, that is x1 and x2, and the function is this x2 plus x1 square minus 11 square plus x2 square plus x1 minus 7. Oh, we just did this, I think. Okay, so this you know that how we can create a function. Okay, next what we are doing, we are keeping this x1 and x2 as two vectors as in the sequence will start from -6 to 6 and with a difference of 0.1. So it will go like -6, -5.9, -5.8, -5.7, and like that it will reach till 6, like 5.7, 5.8, 5.9, 5.9 and 6, right? So now we have created two vectors, that is x1 and x2, with these many elements. And this fp is what? Fp is fp equals outer x1 x2 and fp. So what we are doing, at x1 equals to whatever value is there, and at that value of x2, what is the function value, that is fp. So just whatever x1 and x2 we are just putting that value on the these two x1 and x2. We have created two vectors, right? Now we have elements in those vectors. At those element value we are calculating this fp. Fp is what? Function. So with this, what we are calculating, we are calculating the function value. Okay, so now fp is also a vector with same length of that of x1 and x2. Okay, now we want to plot this. So just run this line first. So function is created, x1 x2 two vectors created, fp we got the function value, right? Now we want to plot that here. So to plot 3D plot, what we used PERSP. Okay, and x1 is the on the x-axis, x2 is on the y-axis, and z-axis is what? fp. Okay, because fp is the function. Theta equals to 30 and phi equals to 30. This represents the rotation. Okay, so in which angle you want to see the function or the 3D plot. If you want to change this, the angle with which you can see the plot will change. Okay, expand at 0.5 and color will be light blue, let's say. Just plot this. What happened? Okay, it was plotting. So see, now we can see this x1 is on the x-axis, maybe x2 on the y-axis, and fp on the z-axis. So this is the 3D plot, right? Now let's say if you want to change the angle that you are seeing, you can just change it to maybe 60 and just let run. See, it will change. See, it's changed, right? So from this angle it changed to 60-degree angle. Now the same plot can be done in contour plot. So what we are doing, we are projecting this 3D figure on this plane, that is x1 x2 plane. Okay, we'll just do that. Control enter. Wait for maybe a few seconds, it will come. So see, so we can see the same plot but in the contour format. You can write x label and y label also as x lab equals to some, you can write all those. Okay, so this one was for figures. Now this contour plot, wherever you can see white, okay, you want to kind of do interpolation or extrapolation, let's say. So in this it will do what? It will reduce. So 10 to 0 it will go. So this function you might have seen in the last class, I guess. So here you'll have one minimum value, here you will have a one minimum value, again here one you will have one minimum value, here minimum value, but here you will get the maximum value, something like that, right? So now we want to do the same plot but with different perspective, let's say. Okay, so for that we'll use plotly package. So plotly is one of the library package that we use very frequently. So for that you need to install this package. So I have installed this package. You can just use install.packages and the package that you are writing. So again you remember that this package or these functions, it is written in whatever form, maybe it is letter sensitive. So if it is in capital letter in the function, you should write that in capital letter only. Okay, so I have installed, so I have just commenting it down. So to use this, what we have to do, we have to call that package. So we can write it as library and plotly. Okay, just control enter, we have called. Now we are creating two vectors. Now all these things I'm not explaining because now you guys know about this function. I'm creating the function is 10 plus x square minus 5x square plus 9y square, or okay, this one will be xy. Okay, and just again z is what? Z is the f5 value. Okay, f5 value we are keeping it in z. Now what we are doing, we are using that function. So function you have to write like this, plot underscore ly. Okay, so plot underscore ly, we are storing that figure in the variable fig. Okay, z equals to z, type is what type? Contour type. Okay, if you just want to check it that how we can write this, so you can just write it plot sorry, plotly. So you will get all these things. So here you can see data equals to data frame. You can create a data frame also, and data frame you can plot whatever you want. So if you don't mention type, it will be null. Okay, so like that, based on that, see, you can use type as scatter also, bar also, box plot also. So any kind of plot, most of the plots that you can visualize, scatter plot, bar plot, box plot, contour plot, everything you can do it here using this function, that is plotly. So for now what we want to do, we want to create the contour map. Okay, so we'll just see. So contour equals to list show labels equals to true, so it will show these labels, that is 10, 20, 40, whatever you can see. We will just run this, and to see this figure you have to write that, or okay. So now we want the color bar also, whatever color we are doing it here, so we want to see the color bar, so that's why I'm writing it color bar, and the title for the color bar I'm keeping it as elevation. Just run this, and now if you run this, that is this fig whatever we have stored, you can see the figure. Give a give few seconds, it will create. Yeah, see, so this is the function. Which function? This is the function of this. Where is that? This one, 10 plus x square minus 5xy plus 9y square plus y. So this is the function. So this is the x label, this is y, and this is z. Okay, and the elevation start from maybe 0 and it goes something like 1400 or something. Okay, I hope this plotly function is clear. Anything, any doubt, any questions till now? You can write in the chat box, or if you want to speak, that also you can do. Okay, if you guys not have any question, I'll move to the next part, that is the particle swarm optimization and all. Okay, before particle swarm optimization we have also seen evolutionary strategies. So in evolutionary strategies what we have seen, that uh, in this evolutionary strategies or ES, what we have seen that, okay, I'll just switch on the video first. So in evolutionary strategies or ES, what we have seen that, so you must have gone through all the lectures, but just to brief about it. So in evolutionary strategies what we have seen that we use the same selection operator what we have seen in the genetic algorithm. So selections operators are like several type of selection operator we have studied, right? So to do that we have seen roulette wheel selection, we have seen proportionate selection, we have seen tournament selection method, and so on. So those selection methods will be there. Only change will be that in evolutionary strategies there will be no crossover operators will be used, or we this crossover we are not doing in evolutionary strategies, but selection operator and mutation operator will be there, and elitism will be there. So what was elitism? That any some of the best solution we are keeping it, right? So that was elitism. So other than the crossover everything will be there. So that was evolutionary strategies. I'll just show maybe the um, ppt maybe. Yeah, let me see. Give me a minute, I'll just open that. Maybe I'm not showing it. Oh, Okay, I hope you can see the screen. So what we were discussing about this evolutionary strategies. So see, evolutionary strategies will use real parameter values. Okay, so we have seen in the genetic algorithm that it can be the encoding can be done using real code, and it can be done by binary coding and so on, right? So there are different encoding techniques and all. So in evolutionary strategies, it uses real parameter value, and it does not use crossover operator. Okay, so it is just like a real coded genetic algorithm, just it is genetic algorithm only, just we are not doing the crossover, and remaining thing whatever we have seen in the genetic algorithm, same it is. Okay, so we are it is the same as the real coded genetic algorithm with selection and mutation operators only. Okay, so it can be two members or it can be different members. So here two members, as in the first one, it shows you the parent, and the second one shows you the offspring. So this 1 plus 1 means what? One parent and one offspring. Okay, so in each iteration one parent is used to create one offspring by using Gaussian mutation operator. What is this Gaussian mutation operator and all, we'll see. Okay, so what we do, so we are choosing a initial solution here. So like the way we have discussed in the classical optimization, that in the beginning we are considering one initial solution and then moving towards the whatever is the global optimum. So like that we will here also will choose a initial solution and one mutation strength sigma. So this mutation strength will come. So what we are doing, we are moving from one initial solution and we will move till we reach the global optimum, right? So let's say the second variable may be y. So y equals to x plus n represents normal distribution or Gaussian distribution. So what we are doing, we are mutating the solution using one Gaussian filter or Gaussian distribution, let's say. Okay, so n 0 means what? This first one represents mean and the second one represents the standard deviation. So with mean 0 and standard deviation sigma, and this standard deviation is called as the mutation strength. Okay, so we are choosing one initial solution and this mutation strength value also will consider. Okay, based on our experience and all, we'll consider one mutation strength value. If you are getting any questions in your exam, the mutation strength value mostly will be specified. Okay, now we have y value. Now for the first one we have the function. First of all we have a let's say one optimization function, right? One objective function. Now at initial solution we'll check the value, because we are checking the function value and we want to know that at what x value we are having the global maximum or global minimum. So for that we'll check fy also. So now if we are fy we are checking, if fy is less than f of x, then what, we'll replace x with y. Okay, so based on whatever whatever we are doing, genetic algorithm on its own, what it is it's doing, it is considered the maximum value. Okay, so if f of y is less than f of x, then we'll replace that with x with y. Okay, now if termination criteria is satisfied, that is this criteria is satisfied, we'll stop. Otherwise we'll again go to step 2. Okay, and then again put other values. For this normal distribution we can just create, okay, we can just generate, and then based on that we can do the solutions. Okay, so the strength of the algorithm, strength of the, so here the strength of the algorithm depends on so many things. See, it depends on the initial solution, it depends on the mutation strength, right? So it depends on both these things, initial solution as well as the mutation strength. And so to understand that, we have one Reichenberg postulate, and this postulate says that if the ratio of successful mutation as in the offsprings that is made to all the mutation should be 1 by 5. Okay, so if this ratio, that is the ratio of successful mutation to all mutation, is greater than 5, then we have to increase the mutation strength, otherwise we have to decrease the mutation strength. Okay, so if you want to, like here you can see a mutation is defined as a successful when a mutation is successful if the mutated offspring is better than the parent solution, right? Now if ps is the ratio that we have seen in the Reichenberg postulate, then this guy, that is Schwefel, suggested that a factor, that is cd equals to 0.817 in the following sigma update will be ruled. There will be a rule that if this ratio is equals to 1 by 5, then we'll keep the same sigma that we have, we will not change the mutation strength. But if it is greater than 1 by 5, what was mentioned, that if it is greater than 1 by 5, then we have to increase the mutation strength. So how we can increase? We can, so here you can see CD is what, less than 1. Now if we divide the less than 1 value, this value will be, the total value will increase, right? So if this ratio is greater than 1 by 5, we'll divide the sigma with 0.1817, and if it is less than, we just multiply so that it can decrease. Okay, so this one was for two members. And let's say if you have more parents and more offsprings if you want, so that means multi-member, yes, we can. So here mu is what, mu is number of population or number of parent, and sigma will be sorry, the lambda will be the offsprings. Okay, so here we are choosing one initial population mu and one mutation strength sigma again. Okay, so in that it is the same that we have seen, just that solution there was one initial solution, but here we have initial population of the mu value. Initial population we have seen in what is genetic algorithm and all, and like that for will create lambda mutated value from this initial population of mu solutions. So like that it is same that we have seen, just we have mu number of solution or the initial population and lambda mutated solutions we have. Okay, so these and all we have gone through. Now let's just see some questions. I hope you can see the screen. Let me check. Yeah. So we'll move to the next questions. This we have seen that 26 was the answer. Now the question is, crossover operator used in the evolutionary strategies is which one? Can anyone just answer? If you can write in the chat box, that is also fine. If you have any answers, you can just let me know. So just now we have discussed that in evolutionary strategies we don't need any crossover operator, right? So any crossover is not required, is not used in evolutionary strategies. So correct answer will be D. It is none of the above. So let's move on to the next question. Next question is, Reichenberg postulate give an idea about, it gives an idea about the ratio of successful mutation to all the mutations, right? So with that, what we do, we change the sigma value, and sigma value was what? Anyone? Sigma value was the mutation strength, right? Remember that if Reichenberg postulate says that if the ratio is 1 by 5, we don't have to change the mutation strength, whereas if it is less than 1 by 5, then we have to reduce that, whereas if it is greater than 1 by 5, then we have to increase the value for the mutation strength, that is sigma, right? So the answer will be B, that is mutation strength. Let's move on to the next question. Okay, now coming to the particle swarm algorithm. So coming to the particle swarm algorithm, we'll just see the slides once. Maybe I'll just download that. Okay, I'll open the particle swarm optimization. Right, so now the second algorithm or the third algorithm, whatever you can say. So one of the important or most commonly used evolutionary algorithm is particle swarm algorithm, right? Okay, So anyway, we have just done the questions from evolutionary strategies. Now coming to particle swarm algorithm. So in particle swarm algorithm is one of the most commonly used um, evolutionary algorithm, right? So in while mentioning the particle swarm algorithm during meta heuristic optimization, you remember that why this is called particle swarm algorithm, because this is mostly inspired by the bird flocking or fish schooling or swarm optimization, let's say. So here particles, so let's say when you consider the bird flocking, right? So their birds, individual birds are considered as particle, okay? And swarm as in a group of birds, right? So swarm is coming from that. So this particle swarm optimization is can solve any kind of non-linear optimization with non-convex, even if it is non-convex problem, even if it is non-linear anything, we can use the particle swarm optimization method to get to the solution or the optimized value. So here, as I said, it is inspired by social behavior of bird flocking and fish schooling and all. So we'll come how it is happening. Maybe I can just do it here. Let me give me a minute. I'll okay. First I have to connect. I'll stop from here. Okay. Is it visible? I don't think. I hope now you can see. Yes. Okay. Mm, a minute. Okay, I hope now you can see the screen, right? Mm. Okay. So what we were discussing? We were discussing about the particle swarm optimization, and as I mentioned that it is mostly inspired by the bird flocking or fish schooling and all, right? So in that what happens, so let's say if you have so many birds, I'll just take this. So let's say you have a group of birds, maybe these are birds, okay? Just don't go my drawing and all. These are some of the birds, okay? Or maybe we should not create like this. mm. So let's say birds are moving in this direction, okay? Something like this. So several birds are there, okay? Those are moving in this direction, let's say. Now what they are doing, they are searching for food, okay? So all the birds don't know about what, so where is the food and all. So all these birds, this group of birds is searching for food in some area. Okay, now, and somewhere one food is there. Okay, so let's say this is the food which bird is going to eat or bird is going to have, these all the birds. So in these birds what they have, that even if one of the birds sees this food, okay, they will communicate with other birds. Okay, and with this communication what they will say that, okay, now food is there, and based on their location, based on the location of this bird, let's say this bird have seen this food first. Okay, now, so these birds, the other birds, they know the location of each of them. Let's say you know the location of each of the birds. Okay, now, so this, all these birds need to come to this food. So what all things is required? The position you should know, or the bird should know. The velocity with which they are flying, that is required. And then now this bird will communicate with all the birds, right? Now this bird has its own individual search. So each of the bird is searching. Okay, each of the bird is searching about for the food, and one bird got the food, that okay, this location food is there. So they, now each of the bird will be doing individual search also, and now based on all the birds, all the, or the group of birds, there will be one global search. Okay, so this global search will be based on all the birds that are there in the group. So let's say if 1 2 3 4 5 6 7 8, so 8 birds are there, and so these birds will communicate, will keep communicating with each other. So now they know the position, velocity. Now each birds are doing the search. It's not like only one bird is there, one head boy is there, and he is only searching for the food. It's not like that. All the birds will be looking for the food. If one guy or maybe one bird is knowing that, okay, here the food is there, so they will communicate with all the birds, and then, so so all the birds are doing their individual search, as well as there is, if someone is knowing the location of the food, then that is that they will communicate globally, or in their search space the whole birds will be knowing then. So that is kind of global search. Okay, so birds will not have any location of the so all the birds will not have the knowledge about the location of the food, but they will know that how far the food is from their present location. So from there the position and velocity comes. Okay, so what happens, so how they will move now? So let's say if this bird is there, right, now this bird will move. Here you can see this one is coming in one direction, so let's say this bird I'll consider. Okay, so maybe I'll create one kind of bird, maybe, and this is bee or something like that. This is feather, and this is maybe something like this. So this is this bird. Okay, I'll write 1 2 3 4. It will be easy. Okay, so now this is the first bird which have seen the food. Now what he will do, how it will move, it will, it will know its individual best. Okay, because everyone is searching, so everyone will have their individual search. Okay, now it will have its own position, and it will move, how it will move with some velocity. So let's say some velocity is there. Okay, and there will be, maybe let's say one global search will be there. Okay, so this one will be global best. So each of the bird are moving like this. It's not only one bird is moving like this. Each of the bird is having one velocity, their own velocity. They are doing one individual search, and they are also doing the global search based on the communication, right? So let's say if the first bird is moving, so first bird is moving, first bird, let's say first bird in 1 hour, they moved something like that. Individually he searched. Okay, I'll change the color. Individually he searched, maybe let's say some part, maybe let's say 1 kilometer. Okay, then he will have its own velocity, let's say, so it will move in the velocity direction maybe for 1 kilometer, and it will also have one global direction with 1 kilometer. So like that, every each one of the birds, maybe this one bird will move with its own velocity. Okay, maybe velocity is in this direction, so I should not write like that. Okay, so it is moving in its own velocity, maybe v2, let's say. So this one is v1, let's say. Okay, v2 velocity, then it is also doing its individual search. Okay, and so this individual search is the personal best, because each one of them will be searching, right? So this one will be personal best, and then they will have one global search also. So let's say, so this is the global search. Okay, like that all the birds will be doing. So based on that, a big area will be covered. Okay, and because of this communication, they will reach to the optimum location where the food is there. So at the end, they will reach to this food. Okay, so here what all we have seen, we have seen that every each of the birds or each of the particles. So as I said, these birds are considered as the particle. Okay, so each of the, so these birds, how we can use that in our work. So whatever we are using this process, or let's say this behavior of the birds, right? This behavior we are just copying, and we are solving our function, the optimization function, right? So we are optimizing our problem using this kind of behavior of the birds. Similar kind of behavior fish schooling also do. So in that also several fishes are there. Each of the fish will be doing their individual search, and in that, if some fish is getting the information about where the food is there, that will be communicated to each of the fishes there, and like that. So like that we use this process in our problem to optimize the function, right? So here birds is called the particle. This means in our case, the solution that we are considering is the particle. Okay, and all these particles will have its own fitness value, and this fitness function is called as objective function, as we have mentioned in the previous classes, right? So this fitness function need to be uh, checked for whatever limits are there. Okay, so all the particles, what they will do, they will preserve their individual best performance. That is uh, best performance, as in, so let's say 2 3 people are there. Here we have, let's say now we have 4 people: Nimai, Mr. Chetan, Ritendra, and I am there. So let's say we are 4 people, we have a team here. Okay, so now we have one location, and we know that somewhere in this location, so there is maybe so many mountains and all are there. Okay, so I am plotting some contour plots, something like this. Some contour plots are there, and we know there is some jewelry and maybe some khajana is there here. Okay, so this is jewelry and all. Now we are all, we four people are there in a team, and every day what we are doing, we are searching for this jewelries and all, jewels and all. Okay, so let's say one starts from here, two is starting from here, three is starting from here, four is starting from here somewhere. So every day each one of them will try their individual best. They will move with their own velocity, and let's say each one of us is having one phone with which we can communicate with each other, let's say. Okay, so every day we will be knowing that what is the global best, or global best as in, so let's say we know that this jewelries or whatever jewels are there is at the decent location. This means at the minimum point, or the deepest valley. Okay, at that point these jewelries are there. Okay, so every day we are moving, and we are knowing, okay, this day we are having we have reached maybe -5 meter level, something like that. Okay, so every day we will be knowing that, okay, this is the global best. So out of four member will be going every day. uh, Morning will start, evening will end, and after that, let's say we'll meet, and then we'll have fun, eat and all. So that time we'll discuss that I have reached -5 meter. Yeah, someone will say I have reached 10 meter, the minimum I'm saying in the case of mountains or valleys. Okay, so someone will have its own global best, so we'll know the information about the global best. Everyone will have their individual best, and hence everyone, maybe second day if we are going, we'll know, okay, this location we have our individual best was this. So we have a memory also. So individual best, say what I mean, that we have memory, and hence we are using that every day. Okay, so we have the individual best performance. This means memory it is having, then we're also having the global best or the best performance of this group. So this 4 people ka team is there, right? In that, what is the best performance in that day? Okay, so we have the global best so that we can communicate each other, and hence we adjust our velocity. We adjust our velocity considering that the best performance and also considering the best performance of the best particle. Okay, and hence at the end will reach to this jewelry, something like this. So like this, like bird flocking and all, same process we are using and we are reaching to the jewelry. So this is kind of optimization only, right? So here what we have, if so now if we want to write this in the form of position and velocity vector, how will we write? So velocity we need to keep, right? So velocity we will have omega or w into vi. So this will represent the inertia effect. Okay, because we have it's our own velocity, every day will change based on that. Then we are having maybe c1 into some random component, okay, into pi minus xi. Okay, so this pi is personal influence, or maybe as I was saying, individual. So with this we'll know the location of the individual best. Okay, and c1 is one of the coefficient which will come in come later. Okay, so this component is defining what? So here we have seen individual best is also there. Okay, so this is the personal best or individual best. So we are doing local search here, local search as in individual search. Okay, so this means, let's say if 4 people of are there, one is Mr. Chetan, one is Mr. Nimai, one is Mr. Ritendra, and one is Balram, let's say. Okay, now so everyone is doing their local search. So let's say if this much they can cover in one day, okay, then they will move in this direction, maybe within this direction, in this direction. So this is the local search. Okay, so like that everyone will have their own area, let's say. So with this component what we'll get? With this component we'll get the individual search. Now we know, now we are communicating with each other, 4 of us. Now from that we know that where is the global best. Maybe R said that okay, here is the minimum that he have reached, but in our area we have not reached that. So based on this again we'll maybe when we are reaching here, we'll start our local search here so that we can reach the global minimum, right? So like that. So this one is the global search, or sorry, local search or individual search. Other than that, what we have, see, each one of the particle or each one of us is having our own velocity, that is come as inertial effect. Then we have our own area, which is the local search or individual. What is left is the global search, sorry, is the global search. What happened? Okay, now you can see, right? I don't know. Okay, so now what is left is the global search. So again we'll put some other coefficient into some random component into, let's say, sorry, what is happening, into global of that particle minus xi is the position again. Okay, so this is what, this is the global search, or we say it as maybe social influence. This social influence as in, because of the all the team members in the team, we are coming to this c1 and c2 are the two coefficient which we are giving to individual best as well as the global best. Okay, so generally c1 plus c2 is 4, but this is again, it is a general value, it is not required that you have to keep this value only. So this one was the velocity vector, that is how we are updating at each of the iteration, like this, with this um, expression, let's say. And the position is change something like xi plus vi plus 1. Okay, so with this expression we'll be keep iterating and we'll be changing the position. Okay, so c1 and c2, as I said, are the coefficient, and these coefficient are called as Learning factor, why? Because at each of the iteration we'll know that which in individually where is the best, and individually where is the global best. Oh, sorry, not individually. And each iteration will get one individual best and one global best. Okay, and with that we are learning, right? And this W is called the inertia weight. Okay. And remember, when the velocity is very slow, that time the algorithm is very slow, but we will reach to the solution. And again, you can't keep a big velocity. Okay, if you are keeping a big velocity, this algorithm becomes unstable. Okay, so just to note it down. And again, in this there is no selection. And now if you are not doing any selection, right, now the selection operator you are not using, the big part of the evolutionary algorithm you are not doing. Hence, see, so many things we have, the update version of maybe genetic algorithm, you can say. So this method, that is particle swarm optimization, is like faster and efficient, more efficient and more faster as in computationally, if you say, right? So this is the only optimization method or algorithm in which we are not removing any candidate from population. So we are not doing any selection, so we are not removing any candidate population member, right? This will combine both the local search is there, global search is there. Okay, and this inertia effect, in this inertia is effect is considered to balance the exploration as well as the exploitation. It's not like that only the velocity or inertia term is balancing the exploration and exploitation, but the most part from this expression is balanced by the inertia effect. But the other terms, that is local search and global search, those are also balancing the exploration and exploitation. But if you compare with the inertia term, it is somewhat less. Okay, it is simple and computationally efficient and all that I have discussed. So any question on this, like what is particle swarm optimization? Any questions, any doubt? I hope I have explained it properly. Okay, so I hope there is no queries. So just to see that how, what are the steps we are doing, we will create one initial population first. Okay, so we'll create one initial population, what we were doing in genetic algorithm, but this time based on one uniformly distribution over the search domain. Then after creating one initial population, we'll evaluate the position of the particle according to the objective function. Okay, now coming the termination criteria. If the current position of the particle is better than the previous best position, so whatever, in whatever algorithm, what if we are seeing in meta heuristic optimization or whatever optimization you are seeing, what we are doing, we are selecting the best and discarding the rest, right? So like that, if the current position of the particle will be better than the previous position, then what we'll do, we'll consider the current position, right? So like that, we'll update our personal best position and determine the best particle of the population, and hence it will be the global best. So this one is kind of steps which you use in the particle swarm optimization. Okay, so with this I'll move to some of the questions, let's say. This all we have done just now. This one. So the question is, particle swarm optimization or algorithm is inspired by, can anyone give me the answer, please? This is not much thing, simple questions. So as I mentioned, that particle swarm optimization or algorithm is inspired by social behavior of bird flocking, by fish schooling, by swarming and all, right? So the correct answer will be both the social behavior of bird flocking and fish schooling. So answer will be C. Okay, let's move on to the next question. Solution in particle swarm optimization or algorithm, okay, it will be algorithm, is called as okay, solution is called as particle, right? So the correct answer will be A. So the next question is minimize this function 10 plus x1 square minus 5x1 x2 plus 9x square plus x2, and the range is given as minus 6 to 6. But before that, let us do some question related to, or not question, some, where is the shared screen? Yeah, some, we'll see the R code for evolutionary strategies, and then we'll move to maybe particle swarm optimization, right? Okay, I hope you can see the screen. Now coming to evolutionary strategies. So evolutionary strategies, what we have seen, we have seen the that we have seen two member evolutionary strategies, and remember in evolutionary strategies we have seen that no selection operators are used, right? Okay, so in that we have seen two member evolutionary strategies. One is parent, one will be the offspring, and also mu lambda evolutionary strategies, where mu is the initial population of the parent, let's say, and lambda is the offsprings, right, or the solutions you can say. Now let's see some functions. So let's say you have a function that is x1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7 whole square. So you know how to write the function and all, so I'm not explaining those. And these things we have seen. Z outer, as in outer will be the function value. So this function, that is f, will be calculated for each of the values whatever is there in this x1 and x2 vector. So z is the function value and contour plot. So the here no ES is required. If you just run this, you will get what? Contour plots, right? So you got the contour plot for this function, that is x1 square plus x2 minus 11 square, whatever is there, right? So now we are going to give the parameters. Remember, in these evolutionary strategies, what we have seen, the mutation strength, and that is called as sigma. So here I am writing the mutation strength sigma. I'll write it here, that is mutation strength, spelling strength, right? Now we have sigma as 1, let's consider. Okay, and we are doing iterations or generations for 1000 iterations. Number of variables are how much in this function? 2 variables, so we are keeping 2. X naught is what? Initial population. Remember, we have seen that it requires two things: y equals to x plus n of 0 comma sigma, where x is the initial population and sigma is the mutation strength. So sigma we have defined anyway, and we need initial solution, right? So initial solution, I'm keeping x1 as 0 and x2 also as 0. Okay, so this is the initial solution. I'll write this as initial solution, correct? Now we want to see on this point as in x0 of 1 means what? X0 of 1 means the first element of this vector, that is x0 is what? 0, and x0 2 means this value, that is 2. So we just want to plot this point in this contour. Okay, so just run all the lines. So see, okay, I have not run this line, control enter. See, you can see, so here we have point 0 at 0 0, right? At 0 y equals to 0 and x equals to 0, or x1 equals to 0 and x2 0, we have point here, right? Now coming to the evolutionary strategies. Okay, now see, here I am using the while loop. You can use for loop also, no issue. You can use do while loop, for loop, whatever loop is fine. Okay, for loop, I generally use for loop, but in the this lectures sir has used while loop, so just see the while loop only. So what we are initializing I as equals to 1, so I am keeping I equals to 1, some one variable, let's say. So while I will be less than the generation, so how many iteration it will go till maybe less than generation, or if you want to write it as I less than or equal to generation, so it will go till 1000. So while I, that is y is less than generation, it will enter. So now I is what? I is 1, and 1 is less than equals to 1000, so it will enter. Now it entered. Now we are keeping one more variable, that is j equals to 1 we are keeping. Now when j is less than number of variables, so j is how much? 2, sorry, in number of variables is 2, and j is how much? 1. So again it entered. So 1 is less than 2, sorry, here it is not less than, see, it is j equals to, right? So j equals to number of variables, so j is now 2. F naught, we are keeping one variable f naught equals f of x1 and x2. Okay, y we are keeping as x naught, so the initial value we are keeping in y. Now y will change, so y at j will be, so this is the function we have seen in the ES. How we are writing y? Remember, y is equals to, I'll just write it here so that it will be easier for you to understand. Y is equals to x plus normal distribution with mean 0 and standard deviation sigma, right? So this only we are writing it here. Okay, so y equals to x naught j plus r norm as in normal distribution with mean 0 and standard deviation sigma. Okay, now f1 is equals to f of y1 plus y2, y1, sorry, not plus, y1 and y2. Y1 is what? Y1 is simply, see y, what is there? Y is the initial solution, so y1 is the initial solution, first element and second element. Now if f1 is less than f naught, it will enter, and then just like that, you know all this. Why we are keeping j equals to j plus 1 and y equals to y plus 1? So that it can iterate, right? Otherwise it will go in infinite loop, we have seen in the previous class, right? So I'll just run all the line. See, you can see the points are getting here. Should be j less than, okay, sorry, stop it once. I stopped, I'll do it again. So see, now you can see the iterations and the points are moving like this. And as you remember, in genetic algorithm, what it does, it is considering directly the maximum, so we are getting the maximum. If you want to minimize in the function, you can just put 1 minus, right? So it is 1000 iteration, it will go to 1000 iteration and then it will stop. It will take a minute maybe. You'll understand when this is not there, then you will understand that this is done. It is taking much time. Or maybe we'll stop and we'll keep smaller generation so that we can see it fast. We'll keep only 100 iteration, okay? And let's just see like that. Sorry. Okay, it got it, but okay, fine. Now see, points are moving. Only 100 iterations I gave, so I hope it will not take much time. There is some issue, it should not take this much time. Give me a minute, let me check once. Didn't stop it yet. Maybe I'll keep 10 iteration. Hmm. See, it's 10 iterations I have given, so it will also work for 100 iterations. You just wait for 10 15, not 10 15 minutes, I mean 1 or 2 minutes. Okay, so here you can see for 10 iterations it is moving in this direction and it is coming something like this. Okay, as you increase the number of so here what we are getting the maximum value at 3.276 and y equals to 0. And if you just see the function value, it is coming as 13.93. Okay, now if you just increase the generations maybe at 50, let's say, and I'll just do it again. See, again now this time it is moving in this direction and it will create here. Okay, now it's done. We'll just see the values. So the values are minus 3.05 and 0, sorry, and the function value is 103.88. So in this when we have increased the generation, again we have seen that the value is getting more better, more like maximize is get. So this is the impact of the number of generations. Now again if you increase this number of generation maybe to 100, let's say, this time it should work, I guess. Okay, now see, again it is moving in this direction and I hope it will come here only. Okay, it has given, control enter. See, again you are getting something like minus 3.06 and 0, and this one has 103.88. Now this one was how if you change the number of iterations, then how it is changing. But again, what are other things you can change? You can change this mutation strength. So let's say if I am reducing this mutation strength to 0.5, then let's see what happens. Okay, right, see here it is moving in this direction, but it is going more slowly because we have reduced the mutation strength. It has done. Now we'll see the x naught value. So the values are 3.4 and 0 and the function value is 13.27. Okay, now this one how it is changing based on mutation strength. Now let's say if the same mutation strength you have and the same number of iterations you have, but you are changing the initial solution. Let's say you are changing the initial solution to let's say 2 2. Okay, I'll change it to 2 2 or something. Okay, sorry, 2 2, right? And now I'll just run again. Now see, it is starting from 2 2 because we have given the initial solution here and it is moving something like this. But see, again here it is 3 and 2 and this is giving the minimum value. So all this thing will depend. So what initial value you are putting, what is the number of what is the mutation strength that you are giving. So you have whatever, whenever you are doing any optimization using this algorithm, you should have some knowledge about what is the function and how it is behaving, so that you can give the initial solution properly. Okay, now again if you see, if I'm giving it as -1 and 1, okay, let's say, again it will change. See, now it is moving in this direction and the value will again be different. So the value now you can see it is -2.91 and 1. Okay, and the function if you see it is 81, right? I hope this evolution strategies and all is clear now. Okay, that time it was taking much time because by mistake I have here I wrote j equals to number of variables. Okay, now coming to particle swarm optimization. So for particle swarm optimization, the way we have done in the genetic algorithm, what we have used a package of GA. Remember, just to show, I'll show you. In the beginning only, you'll see that we are installing a package called GA. Okay, so this so for particle swarm optimization, again we have to load this package, that is PSO, particle swarm optimization. So I have just installed, and hence I am not installing, I'm just, so just to call, how we will call library, in bracket, in inverted comma, will keep this PSO. So with this it will call the package. Okay, control enter. Now again we are solving this function. So let's say I'm only one function I'm taking. Sorry, what happened? What happened? Okay. Okay, I'm just, okay, I can do that. Let's say I'm only doing for one so only one this function I'm doing just now. Okay, so function is again that same function, x1 square plus x2 minus 11 square plus x1 plus x2 whole square minus 7 ka whole square. Okay, so this is the function, right? Now these things you know, I'm not going into again how to plot contours and all. So I'll just run all this in one line. Okay, so now we have the contour. Okay, maybe I'll do that again here. We'll set a seed so that we can get the similar solution again. Now here you see we are keeping one value, so this is what is the function in plotly. You remember that even if the package was plotly, I'll just show that plotly was the package, right? But the function that we are using in plotly is plot underscore ly, like that. In particle swarm optimization, even if the package is PSO, but the function that we have to write, it will be like this: PS optim, it should be, sorry, PSOPTIM. So particle swarm optimization, so you have to write like this only. Okay, so then see, if you want to just search, you want to see that what is, how you can write this, then we can just use this PS optim, enter. Okay, so what is this particle swarm optimizer? So what it does, it is the general implementation of particle swarm optimization, usable as a direct replacement for optimization. Okay, so how we are using PS optim? Parameters we have to give. What is parameter? Parameter is the vector with length defining the dimensionality of the optimization problem. Providing actual values of parameter are not necessary. If you write NA is also, then also it is fine. You can give the actual values also, no issue. Included primarily for compatibility with optim. So this is also one of the, see, if you just say, this is for optim is for general purpose optimization, but PS optim is for particle swarm optimization. But if values are provided with the lower and upper bound, then the first particle will be initialized to the position provided by parameter. So here we have so many other arguments, right? Function is there, then lower value, upper values for the variables you can give, control parameters and all will go. So like that, again you see some CP and CG is there. CP is the local exploration constant. This means, you remember when I was explaining the local search method, sorry, the particle swarm optimization, there I mentioned C1. So C1 is what? The learning factor for local search for the individual best, and CG is the coefficient for getting the global best. So these are two coefficients. Okay, And so here you will get w also. Remember w into vi we were doing. So this is the exploitation constant. So a vector of length 1 or 2, if the length is 2, the actual constant usually is gradually changed from w1 to w2 and all. Okay, if you don't mention this w value, it will just default, it will take 1 by 2 into log 2. Similarly, if you don't mention cp value and cg value, it will take as 0.5 plus log 2. Okay, and so on. So these are some of the values that you can just see. Examples are also there if you want to just what. So we'll just use our example, that is this function. We'll go to see the plots also. Huh. Now what we are doing, we have set the seed. Let's say what happened, there is some optimization error. What is that? Could not find function. Okay. Huh. Now so now I have kept this ps optim, right? So this is the function f that we have created. Lower value for the x, I am keeping it as -5 and upper as 5. So these are the lower and upper bound of the variable. Then control, in this control we are listing the absolute as 1 e to the power minus 8. cp is 0.5, c9 cg as 0.9 we are keeping. So you can change this also, the coefficient, and check how it is happening. This hybrid is what, as we know in meta heuristic optimization, whatever we have learned till now, it is not giving the exact optimal value, but it will give very near optimal value, right? It will not reach the, sometimes it will reach, but most of the time it will give you the near optimal uh, solution. Okay, so now if you want to reach to the exact optimal solution from this near optimal solution, what you will do, you will again use the classical optimization or the gradient mesh method, right? So for, if you use this particle swarm optimization, maybe for faster calculation, or maybe for more efficient way, so in the beginning you are using this particle swarm optimization, and just at the end when you want to reach from to the exact optimal solution from the near optimal solution, what you will use, you will use any of the gradient mesh method, any classical optimization, let's say. So in that case, that process is called as hybrid optimization, right? So here hybrid equals to off means we are not doing any gradient based method. Okay, so we'll just run this. Okay, now if you want to see all these points, okay, so this will make a point. So now you can see the point is where with this optimization we have reached the point as here. Okay, so if you just want to see the residual points, see the values are 3.584421 and x2 is minus 1.848. Okay, again the count iteration and all, if you want to just see. Now let's say if you want to change this. Okay, I want to make the individual based constant as 1.5, and let's say this as 3.5 or maybe 2.5. Okay, and we'll just do the whole thing again. Let's say, see again we are getting points here. So like that, if you just run again, maybe